Welcome to today's webinar with the title Now It's Getting Hot, Polymer Resistors and Heaters. I am Andreas Schilp, the host of today's Würth Elektronik Circuit Board Technology webinar, and I would like to welcome you. The speaker in today's webinar is a qualified specialist from Würth Elektronik Circuit Board Technology, Andreas Dreher from our Technical Project Management. Welcome, Andreas. And now I wish you lots of fun and new information.
Thank you for your kind introduction and a welcome also from my side. As announced under the title, we would like to take a look with you to the new printed polymer samples. During a lot of great discussions with customers on the S&T trade fair in Nuremberg this year, I noticed that not everyone is aware of the diversity of this technology, even though it's already being used since ages. Really, the first PCB produced shortly after the Second World War already used printed polymer technology, so it's pretty old. Since then, the printed polymer technology and also the printed circuit boards, of course, have evolved and can be used now in many different areas. But before we go into more detail about printed polymer, let introduce me myself. I'm since 2003 at Würth Elektronik and was before still on the same facility in Schopfheim. I've been involved in various areas at quality assurance and in the technical development of different processes. I dealt with a lot of different qualifications of base material, used many different reliability tests, and was also involved in the development of the new inkjet technology for solder mask for the PCB production. You can contact me with the shown details, and if you wish to add me to your address book, you can use the shown QR code. Let us have a closer look to the agenda for today. We start with a brief introduction of the homepage, where you can find a lot of general information about PCBs and also the polymer. Afterwards, we will have a look on the production, how we produce the printed polymers in our site, and later go through the polymer sample and show you part by part what are the features of our new samples. We close the presentation with some real-world applications and different examples how to use it, and have later a discussion with your answers online here together. Let's jump in. You can find a lot of information on our homepage, not only for PCBs, also our sisters where supply a lot of different components. In the PCB section shown here, you find a lot of different informations. With the webinar today, we start a series of different webinars where we show you the different samples of technologies. So we have some real basic samples, but they are pretty nice for explaining how PCB works. We have a lot of different flex samples to show different technologies and usages. And also we have some dedicated HDI microvia samples. You can find a lot of information there already, and even if the webinars are not online yet, you can still request samples over the homepage. But now let's focus together on the printed polymer part, where we are very interested for the moment. You can find there the description of the polymer samples in details. You can interactively go through the sections and have a look to the different features, and also have some technical recommendations underneath. Also there you can find some general background information and the design guide or some technical webinars for real-world applications. On the samples we have typical resistors or potentiometers. We have contacts and switches. We can include some sensor functions to measure a lot of different areas, and also recreated some heaters on the board. Over the next slide we go through them step by step. As the name suggests, the printed polymer is applied by printing, more precisely screen printing. This is happening in a connected screen printing line, so all the machines here shown are connected via conveyor belts and transport systems. In the beginning, we have to prepare the polymer itself. There are many different products on the market that are dedicated for very special areas, for example, high abrasion resistance, or there are other products that are more generalists for a wide range of applications. The raw pastes can be mixed to exactly meet the customer expectations and make your design work. Mixing also reduces the viscosity. Similar to a solder paste, they have a thixotropic behavior. This means as longer the paste sits, as thicker it will become. So to have a good printing behavior, you have to mix it up to get a really smooth paste which has a viscosity like toothpaste. We print the polymer in the manufacturing panel, which has a maximum size of 610 by 535 millimeters. In order to achieve the necessary accuracy, the screen is aligned with the existing PCB structures on the PCB, using fiducials on the edge of the panels. This happens automatically after a setup process. The print, we will have a closer look on the next slide, and afterwards most pastes require a resting time of roughly 30 minutes, partially for outgassing, partially to get a smooth surface. During this time you can have a quality control. For example, you can visually examine for misalignment or measure the wet film thickness of the polymer paste. The circuit boards are then transported directly with a conveyor belt into the reflow oven, where the paste is cured and receives the end properties. An adapted oven profile is used here that differs from circuit board to circuit board. Important factors are total thickness, copper amount, and also amount of polymer on the surface. The dry layer thickness can be measured after the curing, or an electrical test can be carried out to measure the properties that we met the target. It is possible to run several times through the whole process to combine different pastes on one board. The printing process itself corresponds to a typical screen printing. So the difference between a t-shirt print, a logo print, or your solder paste print in your production is very similar. In the first step, you fill up the screen, fill up all the cavities with the paste, and in the movement backwards, the printing itself is done, where you transfer the paste to the PCBs in the desired shape. This is an automated system, and all the parameters are programmed in so that you receive a very high reliability through different jobs or a lot of boards. With the process shown, we have produced the hand samples, which are now put on the screen here. We tried to squeeze in as many different features on one board to give you a very good experience, but also more is possible in very creative ways. So let's go through them to give you an overview step by step. We have some contacts for push buttons, for example, or switches, very small one, or several steps as shown here in this area. We have potentiometers, either round ones or linear ones. We have typical resistors in different shapes. And on the back side we also realized some nice heaters where you can heat up your board or your components next to it. Also we have included some sensors which we are looking later in detail. So let's start with the maybe oldest function where the printed polymer technology started, push buttons. It is very often used in wide varieties over the years. Typical applications are automotive, like the air conditioning in a car, or remote controls at your television. You can also use this technology to stack up several PCBs and connect them in the set direction without expensive connectors, which we are using since many years for some applications. So how does it work? You have this typical push buttons. They are two different points of contact. You have some button above it, and the contact resistance is influenced also with this partner. So the contact resistance is usually below 20 ohms and is affected, of course, by the surface area, by the partner, and also, of course, by pressure. Several million strokes are possible without any problems. Tested, for example, in the good old times of mobile phones before the touchscreen generation. I'm not sure how I will explain this to the next generation of PCB engineers which are only using the sliding mobile phones today. But yeah, really proven in use over the ages. Similar idea, you have a switch where you have a ground connection, for example, with several contacts where you can slide over and have several different buttons in one. Again, here a typical contact resistance is below 20 ohms and is influenced by the contact partner. More than 200,000 switching cycles are easily achievable with standard sliders, and if you have dedicated sliders, even more. In critical applications, you can also test it and add an insulation between the different pads to prevent shorts when the slider moves over the different areas. We can test this also in our production. So we have a little test machine, which is usually showed in a video, not working at the moment. Let me try to fix it. So we can do some tests in our production where you provide us your slider, and we have a little device which is moving the button up and down, measuring the contact resistance, which is shown in this chart below. Typically in the first few cycles you have a little shift in resistance where the sliders grind each other to the surface, but afterwards the wear resistance is pretty high. The polymer itself has some smearing effect that these high cycles are easily achieved and can be tested if necessary on a lot basis on test coupons. This ensures a high continuous quality level, and it is possible to test it every lot. Of course, the switch principle can also be used for designing a rotary switch. So the mentioned functions on sliders are also working in round shapes or in very complicated shapes, as shown here in this rotary switch. This shows a significant advantage of a technology. The printed structures can be in any shape, in very different sizes, and with different characteristics. Only the creativity and some process parameters are limiting us here in achieving different features. Another nice feature are edge connectors. Typically, you know the edge connectors as shown here with a galvanic gold surface. And due to the high abrasion resistance of a printed polymer and the high resistance to environmental influences, the polymer pastes are very suitable as edge connectors. They are more robust than the standard nickel gold version and are way cheaper than compared to a galvanic gold setup with some extra gold. It can also be used in harsh environments like humidity or corrosive gas areas, proven in offshore systems. Another advantage is that these contacts do not require any galvanic connection, as it is with galvanic gold pins, which are usually separated after the gold plating, and therefore you have some free copper present on this side. This can be avoided by using printed polymer. Another nice feature where we also take the high abrasion resistance of printed polymer is having sliding potentiometers or rotary potentiometers. The properties of the rotary potentiometers are comparable to the linear slide as shown before. You can create linear or logarithmic resistance curves by design. Also, it is possible to create different contact points to have a linear logarithmic feedback on this point. The potentiometers are characterized by a high abrasion resistance and a long service life. More than 1 million grinding cycles are easily achievable, or we have tested with a customer 5 million cycles with mechanical micro vibrations in a 20 Hertz area. So yeah, you really can use them for a long time. Another feature are just signal receivers. So you can print copper underneath the whole area of the potentiometer, and you have very low contact resistance over the whole area. This can be used for telescopic applications, or if you create a round shape, you avoid a wire mess on rotary applications. You use them as a slider to feed some signals through maybe a robot manipulator. This can be done easily with printed polymer. A whole field of applications are around sensors, and this feature is not so well known with the printed polymer technology. Due to the physical properties, you can create various sensors and can be easily implemented in the designs. For example, you can use them as a strain gauge or a temperature or a bending sensor. Let's have a closer look to these ideas. So the temperature coefficient of polymer pastes are negative in general. Depending on the paste, you can achieve different values. So I've brought some typical lines where we tested it from minus 60 degrees to roughly 150 degrees. And it is typically very linear in an area of minus 450 to 750 ppm per Kelvin. If you compare these numbers to a typical PT1000 thermal sensor on a metallic base, it has 4000 ppm per Kelvin. So you see, even with these samples, it's easily possible to measure temperature changes without an additional components on the board. Not as accurate as the PT1000, but pretty good for reasonable applications. Another idea is using it as a bending sensor. So on the sample we have deep milled an area, so it is very thin, and a thin PCB is also a flexible PCB. So you can bend it, and in bending you can measure clearly resistance change. So in our example of a printed polymer sensor, we have a 1.2 kilo ohms starting resistance, and if you bend it in such a shape, the change is already 20 ohms. So it's easily measuring a lot of vibrations, and you can use it as a strain gauge, but of course then you would use a meander structure to higher up the change. Please also keep in mind that strong bending angles, as shown on this picture, are not recommended in real-world applications, but the polymer will not fail. Typically, the FR4 will break before the polymer will fail in such a strong bending area. So today, maybe the most used example is resistors. We can create very different resistor shapes, sizes and values. We have added typical components like a 1206 or 0805 resistors with a size of 2 millimeters by 1.25 millimeters. Smaller designs are possible with some restrictions. So the smallest polymer resistor we printed was 1.6 millimeter to 0.8 millimeters. The printed resistors are ideal as pull-up or pull-down resistance or as end resistors on a terminal block. The untrimmed tolerance of the resistors are plus minus 30%, and you can increase the tolerance or lower the tolerance by laser adjustment, by trimming it down to plus minus 5%. Voltage dividers are more accurate. The divide ratio can be lower than 3% over the lifetime. Also, the resistors can easily be printed also on the inner layers, so you can embed them and protect them from the environment or save some space on the outer layer. A typical design example, you see here two contact points, can be copper with nickel gold on top, and you print your resistors on top of them. The effective area can be a square. In this example, let's take a ratio of 1:1 in length and width. With a 100 ohm paste, you will create a 100 ohm resistor, and in this example, it has a power dissipation limit of 150 milliwatts per square millimeter, or in this resistor. If you need a different resistance value, you can just change the aspect ratio. 2:1, for example, you will have a 200 ohm resistor with the same paste and the same power dissipation. Or if you need a high power component, just change the aspect ratio again. You have a 100 ohm resistors, but with twice of a power dissipation. And with this easily examples, you can create different resistor values and also power dissipation factors on a same board with just one print. As mentioned before, without laser trimming, we have a tolerance of plus minus 30 ohms. To lower it, we have an automated process where we measure the printed polymer in situ, where the laser will cut a little slide into the resistor and trim it down until the final value is reached. This also can be used for traceability. You can program the laser that it will cut an individual binary code, for example, on specially designed resistors, and create an individual traceability which you can measure by electric systems and in the electric mode. To sum up the functions of resistors, a wide variety of form factors are possible. You can adapt them also to very complex PCB shapes, as shown in this area. You can use them really from low resistance, low than 10 ohms, up to really high resistance in the giga-ohm area. You can use them for high voltage applications, for test probes on railway overhead lines, or to use them to get rid of high voltage spikes in motor applications. The typical polymer film thickness is around 20 to 25 microns, so it can be easily printed on the inner layers or directly contacted to heatsink, to housing by some adhesives. Also, a very nice feature which gives us also the topic for today's presentation is heating. Let's get hot. With heating applications, different applications are necessary, and typically in PCBs we try to get rid of the heat. Why should we heat up the PCB in the first place? There are some use cases for this, like quartzes, which are temperature resistance, or analog to digital precision devices, which are also affected by temperature. If you heat them up to a defined temperature and keep it at this temperature, you can increase the precision of these measurement devices, which can be done very simple with the heaters on the board. We tested it in our lab, so we connected some wires to the structure on the one hand side where the mander, on the other one we have just a round shape, and you can easily feed them with some voltage. In our example, the mander was fed with 50 volts and it was very fast at around 80 degrees, or the round structure with a different design, just with 6 volts you can easily achieve 100 degrees. The temperature can be very easily adjusted with the polymer paste choice and the layout. So this is the same paste in both applications. Just by design you can very easily create different heating levels with different temperatures, as shown in this chart. So let's have a look away from the samples. We have shown all the features of the polymer samples, how to use them in real-world applications. Contacts buttons are everywhere present, but as I mentioned, you can also use them to stack up several boards together. So in this application, the need was to protect the main board for manipulation. So they created a housing with additional PCBs, and the interconnects between these boards were done with this polymer contact points. When you open the housing and you open, in that case, the contact, the memory of a chip will be erased and you cannot manipulate it. Another feature which we also very intensively explained in this tutorial, printed resistors on high-performance PCB systems, which you can find on our homepage online. We have done this in a very big amount of PCBs over the last 10 years. We produced reliable resistors for a truck application where the resistors were printed on the backside and directly attached to the aluminum heatsink to get rid of all the heat very effectively. It is a very high operation temperature at around 120 degrees with peaks up to 150 degrees where our polymers had a pretty good power D rating. Also mentioned before, you can use it as high voltage applications. In that case, to ground the power lines of a train, that nobody will be hurt by the high voltages in this area. So after all this information, maybe you want to get your own sample. You can very easily require one from our homepage. You can either scan the shown QR code on the sample or use the shown homepage to order with a simple form your own sample, and we will send them over in the next days. So, to finally wrap up, we have a quick question. I mentioned one feature on the sample, not in detail, and I want to have your ideas. What do you think can this structure, this C-shaped structure, can achieve? And I will be happy to get your feedback, and I will hand back over to Andreas.
Yeah, thank you, Andreas, for the detailed presentation of the polymer hand sample and the interesting applications. So this time we do not perform a poll as in the first poll, as we want to know your individual idea. So please use the question field to type in your idea for this C-shaped circuit you can see here on the screen. So I'm really excited about your ideas. Let's wait a few seconds. What do you think? What can you perform with this design? Which kind of sensor type or detection could you use this design? So first idea is a strain gauge. Okay, some sort of torque or rotational sensor, maybe. Thanks for this great idea. Do you have other ideas? So, to be honest, this is a design feature just to activate your creativity. So, heat control with rotation, okay. Some sort of torque or rotational sensor. So I see you're actually have started thinking about using this kind of design, and we would really like to discuss your ideas with you in a project. So thanks at this point for your ideas, and I will hand over to Andreas Dreher again to finish his presentation.
So thank you. Yeah, this is very interesting design features, and thank you for Michael Mattes of designing all this. Our internal layout guy with his team in the background. So if you want to have more details, our focus today was really the sample itself, to explain you what it can be used for or which applications can be used. Of course, definitely more is possible. You find additional infos in our design guide on the homepage. And also, if you want to start some projects with us. The contact is again showed on the screen. So this will wrap up our presentation, and I'm looking forward to your individual questions in the following live session.